In the previous video, we posed this scenario for which the Bode stability criterion cannot be used because the system has more than one critical frequency, or more than one frequency at which the phase angle is equal to minus 180 degrees. Nonetheless, we can still use the frequency response analysis to determine the stability of this process. We just have to apply what's called the Nyquist stability criterion instead of the Bode stability criterion. The Nyquist plot is a plot of the imaginary part of the open loop transfer function versus the real part of the open loop transfer function in the complex plane for different values of omega. In polar coordinates, it corresponds to a plot of the amplitude ratio versus the phase angle, where the amplitude ratio is the distance from the origin and the phase angle is the angle made with the real axis. The Nyquist stability criterion states that for an open loop transfer function that has no unstable pole zero cancellations, the closed loop system is stable if and only if the number of poles to the right of the imaginary axis equals minus the number of times that the point minus 1, 0 is encircled in the clockwise direction by the Nyquist plot. If we assign p equal to the number of right half plane poles in the open loop transfer function, and n equal to the number of times that the Nyquist plot encircles minus 1, 0 in the clockwise direction, then z, which is the sum of n and p, must be equal to 0 for stability. Z counts the number of unstable roots of the characteristic equation, and that's why it must be equal to 0. To show what a Nyquist plot looks like, let's consider an example of an open loop transfer function that we've already seen, this third order transfer function for three different values of the controller gain Kc equal to 1, 4, and 20. We looked at this Bode diagram in a previous video. To construct the Nyquist plot, we begin at the low frequency asymptote, where the phase angle is equal to 0, and the amplitude ratio when Kc is equal to 1 is a value slightly greater than 1. That value is shown in the blue trace here on what we call the Nyquist plot. As we increase the frequency, the amplitude ratio, that is the distance from the origin, stays constant while the phase angle begins to decrease. Since the phase angle is decreasing, the curve is moving in the counterclockwise direction, albeit at a relatively constant distance to the origin. As the frequency continues to increase, the change in the phase angle begins to accelerate, and the amplitude ratio gets smaller. That is, the distance to the origin is getting smaller. And this blue curve is approaching the origin as the phase angle approaches its high frequency asymptote of minus 270 degrees, which cannot be seen here without zooming in. Similar plots are shown for Kc equals 4 and Kc equals 20. These all have the same phase angle, but different values of the amplitude ratio, or different values of the distance from the origin. If we zoom in on this region around the origin here, showing the point minus 1, 0, which is marked with the crosshair here, we can see that when Kc is equal to 1, the Nyquist plot goes between minus 1, 0 and the origin. But when Kc is equal to 4, the Nyquist plot goes right through the point minus 1, 0. That's the point at which the phase angle is equal to minus 180 degrees, and the amplitude ratio, or distance from the origin, is equal to 1. When Kc is equal to 20, or in fact for any value greater than Kc equal to 4, the Nyquist plot will encircle the point minus 1, 0 in the counterclockwise direction, one time. And that makes this process unstable for Kc greater than 4, but stable for Kc less than 4. Now let's use the same type of Nyquist plot to look at our example from earlier, which failed to be analyzed according to the Bode stability criterion because it had three critical frequencies. The Nyquist plot for this open loop transfer function is shown here at three different magnifications. At the largest magnification, we can see that the Nyquist plot begins at very low frequency with a negative real part and a negative imaginary part. And then it approaches the origin. As we zoom in, and again we have the critical point marked with the crosshair here, we see that the Nyquist plot encircles the critical point in the clockwise direction one time, but then encircles it again in the counterclockwise direction another time, before approaching the origin, as the amplitude ratio is getting very, very small. This counterclockwise encirclement of the critical point at -1, 0 stabilizes this open loop transfer function. Like the Bode stability criterion, the Nyquist stability criterion is based on the open loop transfer function. Recall that the methods from chapter 11, such as the Routh array method, require analysis of the characteristic equation. Now, most processes are open loop stable, that is, P is equal to 0. Or the number of unstable poles is 0. Therefore, the closed loop system will be unstable if the Nyquist plot encircles the point -1, 0 one or more times in the clockwise direction. Now, if the Nyquist plot encircles the point -1, 0 in the counterclockwise direction, this contributes a negative value to n. And each counterclockwise encirclement of the point -1, 0 can stabilize one unstable pole. The Nyquist criterion is superior to the Bode criterion in that it is applicable to open-loop unstable processes. And it's also superior to the Bode criterion in that it can be applied when there is more than one critical frequency or gain crossover frequency. However, the Bode diagram has one advantage over the Nyquist diagram in that the Bode diagram shows the frequency explicitly. Now, on the Nyquist diagram, this curve represents a locus of points where each point represents a different value of the frequency, but we can't see those frequencies because the frequencies aren't labeled, whereas in the Bode diagram, the frequency is one of the axes. Earlier, we introduced the gain and phase margins as quantitative measures of the stability. The gain and phase margins can be seen from the Bode diagram, and they can also be seen from the Nyquist plot. In the Bode diagram, the gain margin is the reciprocal of the amplitude ratio at the critical frequency. And the phase margin is the distance between phase angle at the gain crossover frequency and -180 degrees. Similarly, in the Nyquist plot, the gain margin is the reciprocal of the distance to the origin where the Nyquist plot crosses the negative real axis. And the phase margin is the angle made by the point at which the amplitude ratio or distance from the origin is equal to 1 and the negative real axis. This angle is the phase margin, and this reciprocal of this distance is the gain margin. So the quantitative measures of the relative stability can be determined from either the Bode diagram or the Nyquist diagram because they contain the same information. But we should watch out for unusual behavior. Consider a system with a Nyquist plot like the one shown here. This system has a relatively large gain margin of 2 and a phase margin of 45 degrees. That means that you could multiply the gain of the open loop transfer function by a factor of 2 before the system becomes unstable. Or you could add a substantial amount of time delay before the phase margin becomes 0. However, if both the gain and the time delay are slightly increased, then this little loop here might encircle the point -1, 0. So this process is not very robust because even though it has large gain and phase margins, the Nyquist plot curve comes very close to the point -1, 0. Before we finish chapter 14 and appendix J, we'll introduce some quantitative measures of robustness that have to do with how close this Nyquist plot curve gets to the point -1, 0 in the Nyquist diagram.